Hello everyone in CSC-121, Graphical Python Programming. This is the last module of the class. It is also the one that is, for me anyway, the hardest module to teach. I think a lot of people would have trouble covering this material. It is material that honestly I did not even receive in graduate school. So working on a master's degree, the material that we're looking at in our final module of this class is not even something that was covered there. So it is probably some of the material concepts, ideas that will really change the way your programs run. So it's very important. So what are we talking about? We're talking about threading and multiprocessing. Threading and multiprocessing. So loops are everywhere in computers. In CIS-115, usually the first class that most of our folks at community college take, in CIS-110, you were exposed to something similar to this graphic. It is the fetch, execute, and decode cycle that your CPU, your central processing unit in your computer, goes through. This is a cycle. And this, to use an analogy, if you've ever been in a car that had a tachometer or a motorcycle, and you could see how fast that engine was spinning over. This is how the spin cycle of your CPU and your computer. And they measure that nowadays in gigahertz. So if you're looking at a computer that has a rating of 3 gigahertz, that's how fast the CPU runs through this fetch, execute, and decode cycle. And as you can see, it's a loop. And that brings us to the title that I did for these slides. And honestly, there weren't any slides for this material anywhere to be found, so I had to make my own slides, which took a lot of time. So this is the loop that's built into your CPU, and as you probably know, most CPUs nowadays have multiple cores. So just like you could have an airplane that had a single engine, you can also have airplanes that have 2, 3, 4 engines. And so the reason they started putting multiple cores in CPUs is they got the cycle running about as fast as they could make it run. So if you can't make one engine run any faster, then the approach was to add another engine so we could keep getting work done faster. Obviously, airplane with 2 engines has the capability probably to go faster than airplane with 1 engine. So multiple engines, multiple cores in the CPU. And so my desktop computer here has i7 in it. And I'm not sure that I can show you the CPU graph, but I'll try. This is Linux, so let's see if we can see the CPU. Yep, here we go. So you can see that I have 8 cores in this processor. There's only one chip in this computer, but you see how many cores there are? There's actually 8 CPU cores in this one chip. So I have 8 engines that each CPU is capable of running something. And you can see the performance graph painting here of all the cores, and they have a different color for each core on the graph. So just keep in mind that most computers nowadays have at least 2 cores, and a lot of them have 4. Most of our classroom computers at RCCC have 4. And then if you have a more powerful desktop computer, then you could see something that has 8 cores or more. So I've got a Windows virtual machine running here in VirtualBox. So you can see it says Windows 10 Pro, and Windows is running in a window on my Linux computer. And this is the Task Manager program in Windows. So if you go into this Task Manager by just right-clicking on the taskbar and then clicking on Task Manager, and that starts this program up. And I'm on the Processes tab right now, and I've got this virtual machine set up where I'm allocating 4 CPUs, 4 cores, to this Windows virtual machine so that we can run things more than one thing at a time. So on more than one CPU at a time. So we'll come back to that in a moment, but I did want you to see I'm on the Processes tab here in Windows. And so each thing that's running as a multi-process is out here, and you can see that my Edge program has 5 threads running. The way Windows does this is the threads run underneath here, so you can see the threads. So we'll come back to the concepts of threads and processes here in a moment. So let's go back to the slide. So we're talking about this cycle that's going on, and we said that we have multiple cores in computers. Well, here's the thing. The software has not caught up with the multi-core processors. For instance, if you start up on Windows, if you start up the Paint program, let's see if we've got Paint over here. Okay, there's Paint. Okay, I just started Paint up, and we should be able to find that here if I go back. There's the Paint app. Okay, there's Paint running, and you can see that it's just got one thread out there. So this is the Paint process, and it's got one thread. We can go look at that process here by taking and clicking on Paint and going to Details. Now, what going to Details is going to do is, when I click on Paint here, it's going to find the actual program that's running in this Details tab. So here we go. Go to Details. Okay. So you see MS Paint running. There's one instance of MS Paint running. So I've got 8 processors on Linux. I've got 4 processors allocated to Windows here, but I've got one instance of Paint. What that means is this MS Paint program can only run on one CPU, even though I've got 4 in this virtual machine. I can only run this on one of them. So it's kind of like you've got this airplane with 4 engines, but we're going to only fly it on one. Okay? Because this program right here is not able to run multiple processes. It's not able to run multiple processes. And how can you see that for sure? Well, if we right click on MS Paint here and we go to Set Affinity, okay, now right now it can shove this program out there to run a little bit at a time. It can only run itself once, but it can run on any of these CPUs. I can drive that by unchecking all processors and saying I only want it to run on one of those CPUs. And what that means is that when Windows puts it out there to run, it's only going to go to that one CPU. It's not eligible to be processed on any of these others. Okay, now let's look at a program that's multi-processing instead of a single process program. Think I've got Chrome here on Windows. Let's see. Yep, there's Chrome. So watch what happens when I start Chrome up. Okay, now I've got Chrome cranked up here. Okay, now if you look at this right here, look at how many instances of Chrome popped up. And if I right click and let's see, right click and go to details, how many Chrome EXEs do you see out there now? 1, 2, 3, 4, 5, 6, 7, 8. So it put 8 instances of itself out there. And so this program is designed to take advantage of all those CPUs. Okay? It's designed to take advantage of all those CPUs and use that power. The Paint program that we were looking at, if we go to the details on it, there's one instance of Paint. So Paint can only ever run on one CPU at any moment in time. Now Windows can put it on different CPUs. As you saw, it's eligible to be run on different CPUs, but it can only ever run on one of those CPUs at a time. Chrome, on the other hand, because it knew how to multiprocess and was written to multiprocess, Chrome can run on 8 different CPUs simultaneously. Not spread itself, but actually run on 8 processors at once. Okay? So hopefully you're starting to see the power that we have here. Okay? If you know how to write programs that multi-process. Now, there are 2 concepts here. One is multiprocessing and the other is multi-threading. So a lot of the Microsoft programs have been made to thread themselves. Let's start Excel or Word. Let's do Word. Word. Here we're starting Word up. And I'm going to go ahead and just create a blank document. And so here's my Word program running. Now remember, we've got 4 processors here in this Windows virtual machine. So we've got 4 engines that we could run on. But if you wanted to do a spell check on Word, okay, let's go to the task here, you see it's not letting me, when I right click on this, it's not letting me go to details. I have to go up here to the word parent task, and then I can go to details. So how many instances of Word do you see out there? One. Only one instance of Word. So you know yourself that we could have multiple documents open, right? So here I've got two documents open now. I've got document 1 and I've got document 2 open, okay? But if I go to Task Manager and look, how many instances of Word do I have? Just one. Just one. So Word can thread itself, okay? Threading is like time sharing. If you know what timeshares are at the beach, okay, the idea with a timeshare is you have this one beach house, and you get a bunch of people to go together to buy that house, and you say, okay, we've got 20 people that went together to buy this timeshare, and each one of those 20 people is going to get so many weeks a year. What does that come out to? A little over 2 weeks a year that you can have that house to yourself. So we've got this Word program running, and it is threaded, so it's doing timeshare. It can only ever run in one place at a time, but it is threaded, and so because it's threaded, it gives you the illusion of running two things at the same time, even though it's really not. Now if we go back to the tabs here, you saw I have two documents open. So Word created a thread for each document. A thread is a lightweight process. It does not have the capability to run two copies of itself at once. It can timeshare. In other words, you remember that cycle that we were just looking at, the fetch, execute, and decode cycle here that's running? It gets so many seconds of the time as this thing is running. Okay, so it does timeshare. That's what a thread does, is it gives you the illusion. But the difference is that this is only using the power of one CPU at a time. Even though you've got 8 CPUs, it can only ever use one of those CPUs at any given time. So back to flying the 4-engine airplane on one engine. Okay? So Word is threaded. It's not multi-processing. Okay? So let's just, we'll stop after this on the looking at the task, but let's try Excel. So here I'm going to open up a workbook in Excel, and I'm going to open up another one. So I have two workbooks in Excel running here. Let's go to the, so here we are on the Processes tab, and you can see I have 2 threads, okay? And Excel would be a really good candidate to do multi-processing, because you're doing some heavy, you can do some heavy-duty calculations. Yeah, I'm sure some of you have probably seen workbooks that had, oh, I don't know, 20 different sheets in them, and they had to recalc all those sheets. Calculations use the CPU a lot, okay? So Excel would be a great candidate to do multi processing, multiprocessing. But as you can see here, when I go to Task Manager and I go to the and I right click and I go to Details, how many instances of Excel do I have running? Just one. So Excel doesn't multiprocess either. Excel is just doing threading. So there are a lot of opportunities moving forward since we have these multi-core processors to rewrite programs to do that, to use multiple processors at one time instead of giving you the illusion that things are running twice. Those two workbooks were not actually running twice. They were doing the timeshare thing like we were talking about at the beach, where you had one house and each of those cycles that we were looking at back here and fetch, execute, and decode, each of those cycles we were given so many weeks out of the year to one family and so many weeks out of the year to the next family. So now that we've talked about that a little bit, I hope you can see that if you want to use the real power of all those CPUs, that multiprocessing is the way you can do that. Now, whether you actually need to multiprocess is a different thing. That's a different conversation to have. Okay, so let's look at an example of doing this with Python so you can see how this works out. So here I've got, and we'll actually write this program, but I've created a program that we can use that's doing Qt. So it's got a lot of things going on with it. We'll run this program and see some of the reasons why that you might want to thread or you might want to multi-process something. Okay, so all right, so let's go to another drawing that I did here. So that's not the one that I want. I want this one. Yeah, this one. So I had to draw these myself, so pardon the artwork, but that's as good as I could do. So this is what we have been doing with Qt to this point in the class. So let's talk about that. There was a module where I talked a little bit when we were using timers. I'm sure you remember the Q timer with Qt, and I talked about this event loop right here that's in green. I talk about this event loop, and basically let's talk about the whole thing here. So Windows is running this blue loop that we have going on here, simulates our Windows kernel. So Windows has its kernel, which is a special part of the code that runs all those tasks that we saw in Task Manager. It devotes so much of its time to each of those tasks. When we start a new program or a new app, we get one of these green loops running, and you can see that of this whole cycle that Windows is doing, we're getting this much time to run our program. And so our Qt programs have a built-in loop in them. when you start that code at the bottom of the Python file, when we're running those Qt or writing those Qt programs, that code at the bottom that has w.show and it starts the Qt application up, that actually cranks up this green loop. So this is called the event loop. And what that loop is doing is it's sitting there running over and over, and it's checking every time through the loop to see if you've clicked a button or if you've dropped a list box or anything that you've done in that program, any of those things that you could have clicked. The event loop is actually going out there and it's checking all those things each time through the loop. And if it finds one that it needs to do, let's say that you had a button on your dialog and the button was to go print something, or the button was to, calculate something. Well, it would get that button click, and then this red box would have, simulate that task that it needed to do, whether it was print something or loop through, like our MPG program, to loop through printing off you drove for this many hours, and it's got to print each hour out and how far you went, the distance traveled. So that code, when you click that button, actually stops. Yeah, you heard me right. It stops this green loop from spinning. It interrupts that loop. And this loop, the way we've written this program right now anyway, the way we've been doing up till now, when it stops, you can't click anything else. You can't click anything else. Nothing else is going to respond. It's going to stop until everything in this red box or rectangle is done. Okay? So I put that in the notes down here. On Windows especially, the GUI event loop will be interrupted. This green loop right here is going to get interrupted until the task in the red rectangle here finishes. It blocks the event loop. Now, a lot of folks don't even know how to write programs that thread. I seriously doubt that you'll have another class at RCCC, and maybe not anywhere, where you write a program that's threaded. Okay? But what happens is this can block this green loop from running, and you'll get that hourglass on Windows. And I'm sure you've seen this. You've thought your computer hung up. You were running some program, and you got the hourglass, and you couldn't do anything, and you just had to wait until that hourglass went back to the little arrow before you could click on anything. Well, you saw that event loop in that Windows program get interrupted, and it was hung right here in this red rectangle until this finished, and then it could go on. So it blocks it. So let's actually, I've written some code to simulate that, but also here I've got a little graphic of how that would look in time-wise. This line across the bottom is time. And so if we had some function, where we did a def in a Python program, and it had a delay of 1 second, then it would go out here and it would have to run this one function, delay, and then run this next function and delay, and then it would finally get done. So I've simulated that in a program. So let's go back and try it. So this program that we will write has got both approaches. It's got no threading at all, and it's got using a thread pool in here. So I'm going to run it. Let me go to processes here so we can see everything that's going on. And I'm going to go ahead and kill the paint program. So now I've just got Tawny running and I've got the task manager running. Okay, so here we go. Crank this up. Okay, here's my dialog right here. Okay, now you can see we've got Python running here. Okay, and I'm going to do this with no threading so you can see it hang. Now, before I do that, let me scroll down a little bit till I get to the code right here. This count method, you can see all it's doing is it's got a for loop, and it's going to run through this code 30 times. And each time through the for loop, it's going to sleep for 1 second. Okay? And after it sleeps for 1 second, it's going to print that out. So when I click that count button, we'll crank this loop up. And you'll see our application hang. Because if you remember what we have going on here, we've got this green loop is going to be our Qt application with our dialog. This red rectangle is that for loop, that we have running. Okay, and it's going to hang this loop up. I won't be able to do anything else until my for loop finishes if I run this for loop as a single thread. So let's go try it. All right, here we go. All right, so we've got our Python app running here with our dialog. You see it. This is us right here. Okay, I'm going to start that counting going. Ready? Here goes. Okay, it's running. Okay, if I try to click exit, can I click exit? I can't do it. Okay, it's hung up. It's going to have to finish all 30 times before I can exit. Okay, so you can see it's still running. I can't do anything. I can kill it that way. Okay, so we'll come back here and we'll try this again. Okay, now this run no threading right here, what that run no threading is going to do is right here, you see where it says run no threading method right here? This is going to go call an object that is printing out a message with a delay, and it's going to do it 7 times. So it's going to create 7 instances of itself, 7 instances of that object. But because we're not threaded, it's doing this. It's creating this one. This one has to finish before it can create the next one. This one would have to finish before it could create the next one, and so on. So one has to finish before the next one starts. Okay, so this is running no threading. Okay, so let's start it up again. All right, so here it is. Watch down here at the bottom. Thread 1 started sleeping for 8 seconds. It's not really threading at all. What does my dialog say up here? Not responding. What do I have in the window? An hourglass. I can't start counting. I can't do anything. You see, it says not responding. If you look over here, what does it say in Task Manager? not responding. Eventually, all of those things finished. You see where down here we started thread, or well, we called it thread 1, but it's really not threaded. But we started the first one, it slept for 7 seconds, and then it finished. It started the second one, it slept for 6 seconds, it finished. Down here at the end, it took a total of 28 seconds to run through all those things. Where did the 28 seconds come from? Well, here's the delays. 7, 6, 5, 4, 3, 2, 1. If you added all these numbers up, that comes out to 28 seconds. So it did one after the other, after the other, after the other. Okay? And you saw when it was running, I could not click anything inside here when this was running. Okay? Now, I've got some other code out here to do exactly what we did down here, start up 7 things running, but this time I'm going to thread them. I'm actually going to submit these things out to a thread pool, is what they call it in Qt, and those threads are going to run kind of simultaneously. Let me go to the next drawing so you can see what I'm talking about here. Let's see. Drawings. So this is kind of what we will have going on. There'd be more of these threads. If we're doing it 7 times, we'd have 7 of these little red circles that are each going out here and running as part of the event loop. Okay, but you can see that one thread can share some of the time with the next thread if you look at this graphic. Okay, so that's multi-threaded. We could actually have just one thread, and even one thread is better than no threads, because if we have a thread out here, this can run, but it won't interrupt this green loop. This can run, but it's also going to allow this to keep running too. So this circle right here will not block this loop. What'll happen is it'll come here, where I'm tracing my mouse, it'll run around here, and then it'll keep going here. And so it doesn't just stop like that rectangle. It doesn't just stop, and this can't do anything. So threading can make a GUI app much more responsive. You saw an example of what happened if we have this event loop blocked. We can't do anything. We get the hourglass. We get the program not responding or whatever. So threading works really well for things that are not using the CPU that much, for things that just our computer's waiting. For instance, if you're going to a web page to download a file or something, okay, your computer's CPU is spending a lot of time waiting on the internet to do its thing. If you're sending emails out, the email server is holding your computer up while that email is going out and stuff. So when your computer has to wait, well, geez, if it's got to wait, it can just, spin around once, give control to this, wait, spin around, control goes back. So things keep running if you're threaded, okay? Things keep appearing to run, I think is a better way to say that. So if we put multiple threads out here, then we can actually have things that this one runs a little bit, this one runs a little bit, and then it comes back around, this one runs a little bit, just kind of like the time sharing stuff that we have going on. Okay, so let's go back to this program and run it with the copy that's doing threading now. Remember, we did this button that said run no threading? Now let's run this button that says run threads. Okay, so here I'm going to start this up in a second. Let me clear this window down there so you can see, because it's going to be printing to our shell window. That's what I did when I wrote this. So I'm going to go ahead and start the threads running. Okay, now keep in mind, this is going to create 7 threads out there. And if you remember, when we were looking at this, I said this was a total of 28 seconds if you ran these things one after the other, after the other, after the other. Okay? So 28 seconds if you added all those delays up. Let's see how long it takes to run with threading, where we're letting each one of those threads run a little bit as time goes. And also, while those 7 threads are out there running, I'm going to fire up the for loop. You saw I couldn't fire that up before when I had something running down here. You'll see that my GUI, my dialog right here that represents that green loop in the drawing, this puppy is still going to be able to respond to things. I will be able to start this for loop while my threads are running. Okay, so here we go. See, it says all the threads are started now. I'm going to start the for loop running, and you can see this is going on and that's going on, and look how long it took to run all 7 threads. All 7 threads finished in 7 seconds. Just slightly over 7 seconds. So you can see that, and there's our for loop that's still running in the background. So I ran 7 things at once, as well as having my for loop that was still running here in this window, and my GUI kept responding. So this is what we're seeing going on in that Excel and in that Word program, where each time you opened up a new document or workbook, you created another thread. Okay, but remember, all this is doing, it gives you the appearance that this is running. It's actually devoting a little bit of time each cycle to all this stuff. So it spends a little bit of time doing the for loop. It spent a little bit of time doing each one of the threads. Why could it finish in 7 seconds? Because if you look at the code, all the code was doing is it was sleeping for however long we told it to sleep. So it wasn't doing anything. It was perfect candidate to go ahead and give its time to something else. And so everything got a chance to run here simultaneously, threaded, and everything finished in 7 seconds. Where did the 7 seconds come from? That was the longest delay we had. All the other ones were able to finish, and they've all pretty much finished at the same time, didn't they? If you saw, here's our thread 1 started, it's going to sleep for 7 seconds. Here's our thread 6 started, or thread 2 was started for 6 seconds. And you can see all 7 of them finished in slightly over 7 seconds. So, real life story about this. I was doing consulting for a bank in Durham, and they had 6,000 bank branches. And every night they needed to copy the file that had all the transactions that each teller had done. They needed to copy that file up to a server at the central office there in Durham. Well, they had written a program to copy this that was single threaded, which meant if you go back to that drawing that I had at the start of all this single thread right here, this drawing, each copy of that file from those 6,000 branches had to finish before the next copy could start. They had a window of 8 hours to do all that. It took 32 hours for all those copies to finish. So that was when they called me. And I wrote a threaded program because back then we didn't really have multiple cores in CPUs. We had one CPU that could do multiple things at once, threading. And so I wrote a program with 16 threads out there. Each thread was copying a file. Each thread was copying a file. Now remember, when they did it the sequential way, one copy had to finish before the next one started. Well, I did it with 16 threads, which meant I could copy 16 files at once. 16 files at once. And so that program was able to copy files from all 6,000 branches in 4 hours or less. 4 hours. So I took something that was taking 32 hours, which they could not live with 32 hours because it had to finish in 8 hours overnight before the branches opened the next day. So took something that was taking 32 hours to run and made it run and finish in 4. So that's the power of threading and how you can use that. And if you remember, I said that threading works best for things where the computer has to wait on something to finish. Threading is not a good choice for CPU intensive task. Something that's got to do a lot of calculations on the CPU, that's not a good candidate for threading. If you're gonna calculate, recalculate this Excel workbook that has 32 sheets in it, that's some heavy-duty calculations, or it could be. That could benefit a lot from spreading itself over those CPUs to get all those calculations done at once, or almost at once, as opposed to having to wait, for its turn in all these loops. So you've kind of seen how that threading process will work. I'm going to show you one more drawing, and then we're done with drawings at this point. But multiprocessing. Now, at the start of this, I showed you the Chrome program that was spinning up multiple copies of itself. So you remember when we had this GUI event loop here, okay, that Qt event loop, that's a process, okay. I could right click that process and move it to a different CPU, okay. If you spin up multiple programs out here, multiple copies, then you can spread yourself. Each one of these green loops can go to a different CPU as opposed to just running on one. And so instead of just simulating, giving you the illusion that we're doing everything simultaneously. This multiprocessing is truly running multiple things at once. So this is your most powerful way of writing a program, but it's also the most complicated. So multiprocessing, I've got down here in the notes, is a good choice for CPU intensive, what we call CPU bound task, where it's tying up that CPU. It's very complicated to communicate the status of these processes that we're calling them. Notice we're not calling them threads. We're calling them processes because each one of these is a program running. Okay? Each one of these is a program running. And we have to communicate between those programs. If we had this GUI app that's running, we want this GUI app to be able to know when these things were finished or when they sent us some information back. And that is hard. You've got to do that using things like queues or a pipe. Those are two ways that you can have these things send information back to our GUI, is through a queue or a pipe. Okay. Also, when you spin up another process on Windows, each program that runs gets a set of memory, and I think it's around eight. I want to say it's 8 megs of memory for each one of these processes. Whereas when we ran something with threading, everything got that 8 meg and that was all. Okay, so the program stack for these processes, this takes more memory because we're running, instead of running one program that's kind of sharing some time with its threads, we're running 3 programs. So you could see where each program is going to take RAM to run. So this is going to take more RAM. Okay. But think about this. If this were a mission critical program, okay, if one of our processes crashed, it wouldn't take the whole program down. This could crash, this process 2 could crash, but our event loop here, our main program, could keep running. So this can crash, we'd stay up. Okay? Whereas if we were doing threading and everything was in this one green loop, if you crash one of your threads, there's a good chance that you're crashing the whole thing. So and that's what I put down here, that multiprocessing is more fault tolerant. Okay, so that's the general part of this. Now let's go do some of it. Let's go actually do some of this. So first, let's do a threading program. Let's do a threading program in Python. Now, keep in mind that I'm going to show you 2 approaches to threading. The first approach is going to be using the threading stuff that's built into Python. Okay? Now, that's not a good choice to do with Qt. And just so you know, your textbook and I disagree the chapter here on asynchronous programming, the way that he shows doing this is not using Qt at all. Just like in the database chapter, he showed you how to do databases without Qt, and that was a whole lot more work than using Qt. Well, using threading in a Qt app, if you're not using the Qt type of threading, you're setting yourself up to have problems, because remember the green event loop that we were talking about? Your Qt program is going to be running its green loop, and then you're trying to ram some Python threading into the Qt event loop, and that's not a good idea. But I'm going to show you some simple threading first here in Python before we do the threading in Qt, so that we can get the time that things ran. I'm going to import time, and then I'll go ahead and do a start. I'll capture the time when this kicked off. Start equals time dot perf counters is built into the time library, and it lets you count time that is something has been run. And let's make a little function that we can run. I'll call this do something, and we'll pass a delay to it. Okay, so this is a little function. It's taking a parameter in called delay, and I'm going to do a time.sleep, and I'll say sleep for this delay, however long that is that we passed to this function. And then I'm going to print out, I'll use an F string. F strings work really well with databases, and they're just a whole lot easier to use than the old string formatting. This is the placeholder where we will replace that with delay so that we can print out the delay, and then I'll make it go to a new line. So that's going to be the end of that delay function. And then I'm just going to run that function twice so you can see that this is actually just doing one thing after the next. This is not threaded at all. Okay, so we'll just run the same thing twice, and then you can see how long it took to finish. Okay, so what are we doing? We're getting the time to begin with. We have a function here that we create, right? I don't know why it's grayed there, but oh, I know why. I forgot to put my there. Okay, so we created this function, okay? And then here we're going to run that function, and then we're going to get our finish time, and then let's go ahead and print out how long it took to run. Finished in, and we'll round it so that we don't get so many seconds out here. Round finish minus start. Subtract the 2 times. We'll round it to 2 decimal places, and then we'll print out seconds. So this is my F string again, and I need to put my closing placeholder there. So this right here is going to get replaced with whatever this calculation and the run of this function is going to take. So let's run it. Okay. Let's see. So let me click it one more time to run here. Done sleeping 1, done sleeping 2. Nothing surprising. it finished in 2 seconds, right? Because this one had to finish before this one could start. Okay? So now let's let both of them kind of run at the same time. Not quite at the same time. As you recall, if we're threading something, we're doing time sharing. The Python library that allows us to thread stuff is called threading. Okay? And so we can keep this, we can keep that. Our function looks okay just the way it is. Okay? So I've got the threading module. Let's thread these two functions instead of running them one after the other. Let's create two threads. So I'll do that here and then get rid of some of that other code. T1 equals threading dot thread. And then this is where we're going to say the target equals, and the target is the name of our function. And so do something, and notice that I'm not putting the parentheses on the end of this. If you do that, this would try to run the function. You have to leave the function off, the parentheses off. Okay? So I'm passing it the name of the function so that this threading stuff knows to go get this function. Okay? So I'm creating a function, I'm creating a thread that's going to run this function. Now, if you recall, we were passing a 1 to it in here, weren't we, when we ran it? Well, if we're going to thread something, to get that argument to it, we need to do this. It's expecting args. If you remember from argv, when we were in CIS-115, how to get to the command line arguments, they were a list. So we're making a list here that has this number 1 in it. That's what we're passing to that program when it runs. Okay? And basically, if I wanted to have two threads, then I'm just going to copy that line and make this thread 2. And now we're running that same function twice. Okay? It's not actually, we've created the threads, but we haven't actually started them yet. So in order to start them, this is where we actually spin up that thread. So now we've got those two threads that we have started. We still finishing. Now remember, when we ran this with one thread running after the other, it took 2 seconds. Let's see how long it takes now that we've threaded those things. And remember, both of these can kind of share time now, like the time share at the beach. So let's run this again. Both of them finished, and you notice what happened here? I got the finished before I got the done sleeping. This is an important error to understand what happened. Okay? What happened is, as our program ran, it got to the right here where it said start this, and it said, okay, you can go off and run. Start this. Okay, you can go off and run. And then it printed the finish time out down here. And so it ran through that in less, it started both threads, but it didn't wait for them to finish. So if you need to wait for those threads to finish, now there are times when you don't need to wait, okay? But in our case here, in order for our time to be right, we've got to wait for each of these threads to finish. So what we're going to do here is I'm going to put a delay in our program by making our program wait on both of those threads to finish, and you do that with the join special word that comes in the threading library. Okay, so here we go, t1.join. Now our main program is going to wait for this thread to finish. Now if I want to wait for both threads to finish, I've got to join each thread back to the main program. So now we've kicked off both of these threads up here, here, and here, and now we're going to wait for both threads to finish before we proceed down here and print out the time. So you saw before we did this, we were getting this. Okay, now let's see how it responds. Okay, here the first thread ran, second thread ran, and how long did it take it to finish? Because they were waiting, it was able to hand time off, and as you can see, both threads were able to finish almost in 1 second. So before, it was taking 2 seconds when we ran them one after the other. Now we're able to get twice as much done in the same amount of time because the CPU was just waiting around, twiddling its thumbs, so to speak, each time. Okay, so that's how to do threading in Python without Qt. If you're going to use Qt, you'll want to watch another video where we create that program, and we'll do another one. There are two approaches to doing this threading in Qt. But so now I'm going to go ahead and create a multiprocessing program, and we'll finish off. I'm going to use that. Let me make sure my audio is still going. It is. Okay. So I'm going to use that program that we just created. If I can get back to it here, to make a multiprocessing program. And it is very, very similar. That's one thing I like about the way they implemented this with Python, is it's very minor changes to go from threading to multiprocessing at this basic level. So I'm going to start a new program, and I'm going to save this as multiprocessing demo. Multiprocessing demo.py, and it'll be in the same folder as my threading program. So I'm going to take this code that we have already written just a few minutes ago and copy it and paste it into my multiprocessing demo. And so here's a couple, there are a couple main things that have to happen, but of course this one first, we're going to change from importing threading to import multiprocessing. Okay, so I've got that, and now the major change is that we have to have a main function, and we have to have that code that we've been writing all semester long about if name equals main, that's down at the bottom of every program that we've written. And one of the reasons that we do that is so that we can import the code, but this is the other reason. So I'm moving my function up above my code. Okay, so I've got that function now that's called do something, and then I'm going to create my main function. If you don't put a main function in a multiprocessing program for Windows, it will blow. Now, it will run fine on a Mac, it will run fine on Linux, but it will not run on Windows. It'll blow. And that's because of the way Windows works. Functions are not reentrant. You can't re-enter that function twice. It can only run once. So by putting this in a main function, we kind of work around that. So I've taken all the code that we had in the threading and I've moved it into a main function. And now if you recall, most of our main functions, the last thing we did was return at the bottom. And then here's that code that I was just talking to you about. If name equals main, okay, this has to be there or it will blow on Windows. Okay, so we've added this at the top, replaced the threading import with multiprocessing. Now, everywhere that we say threading.thread, we're going to have to change that, say multiprocessing.process. Okay, and then it probably doesn't make sense for us to have T, because remember we had threads before. Let's make it P for process. You notice I'm not changing very much here. Okay, so now I've got the multiprocessing, I've got process, or P1, P2. That's about the extent of the changes that we made from this threading program that we had here, where we were saying threading.thread. We're now saying multiprocessing.process. And of course, we changed our import up here and we made ourselves a main function. So if you recall, when we ran the threading program, we were not creating another instance of Python. If I can get my task manager system monitor up, okay, you can see right now I've got 2 instances of Python here. Going to change this delay so that it's 10 and maybe 15 seconds so that these will hang around long enough for us to see them out here. And so now these, I've changed the time, so where we were just delaying for like, in the threading, I think we had it like 1 second or something. But anyways, I've got them, I changed it in the wrong place. That's what I did. Okay, both of these were 1 second here. Let me go to multiprocessing, change that to 10 and 15. This is going to create more Python programs out there running because we're creating a separate process for each of these. So we should get at least 2 more Pythons out here running when we run this. Let's try it. Yep, you see them out there running? 2 more popped into place down here at the bottom. So those are out there running for that one. First one finished in 10, and then I had another one at 15 seconds. So you can see took a total of 15.01 seconds to run both of them. So that is multiprocessing with Python. Now there is a little bit better module, a newer way to do this. And I'll show you that just because it makes running multiple processes a lot easier. You know how I had to do P1 and P2 and all this down here. we could actually do this with a loop. And so I'm going to save this file as a different file name. I'll call this concurrent futures.py. And so instead of using the multiprocessing module with Python, this newer one that came out in Python 3.2 and after, so it's been around a long time, so to speak, in computer world, concurrent.futures. This makes working with multiprocessing a little bit easier. So instead of having this code right here, I'm going to get rid of all that code and show you how we can run stuff multiple times. So with concurrent.futures.process pool executor as executor. This lets us run a bunch of stuff with this context manager. So this simplifies our work a good bit. I'm going to create a list called seconds, and I'll put in that list. You remember how with the queue threading stuff, I had a bunch of delays out there. So that's what I've got in my list. I'm going to create 5 processes. I'm going to run the first one 5 seconds, the first one 4, or excuse me, the second one 4, third one 3, fourth one 2, and so on. So we're going to end up with 5 instances of Python out there running. I'm going to create a results array. This map function is real handy. Let me explain what map does. It's a really nice little function. Map says take this list right here and map it, and each time through the list we'll get a item. Our executor will add an item for each one of these seconds out here. So it's going to map each element in this seconds list to a new process. So it lets me very easily have this list say how many processes I'm going to put out there, and it's going to map a new process to each element in that list. Okay, so we're going to end up with 5 processes out there. So once that's spun up, we can just wait for those to finish. So we'll put ourselves a for loop out here to check that. For result in results. So we won't get our results until all these things have finished. It'll wait on them. Remember, we had to do a join, doing it the other way, the older way. Without doing a join, we can wait on them right here. And so that's the changes I think that I need to make here to do this the new way. So again, we should see 5 instances of Python get spun up out here. I'm trying to see where my, okay. So right now I've got these 2 instances right here. Okay. We should see 5 more of them drop in my task list here when I run this. So getting 5 things done at once. Okay. So you can see them over here. Whoops. I'll have to start this again because I clicked in there. They went away too fast. Okay, so you can see that they all finished in 5 seconds. So they were all running simultaneously. But let's watch those Python processes spin up here again. Let me get this in the right order. So there that is. And then let me move that over. Okay. Whoops. Okay. So let's try it one more time so you can see these things show up in the task window. So creating 5 separate instances of Python out here, doing 5 things at once. Okay, here goes. See them all? There they all are out there running. And then they finished. And there's our everything finished in 5 seconds. Now, if we wanted to see this actually print the result right here, instead of doing this print from the task, I could actually, you notice I'm printing result down here. So let's do this. Now I'm going to return that, and I'm going to let the printing happen down here so I won't get the nones coming out. Okay, so we'll clear that shell and run this again, and now you'll see the once it finishes, you see done sleeping 5, 4, 3, 2, 1, and finished all in 5 seconds. So we've talked about a lot of stuff in this video. There are 2 more videos coming your way. The next video will be on doing threading with Qt with the thread pool, using the program here that we were playing with in this lecture, so you can actually see how to create that. And then we'll do another version of that program that actually downloads a bunch of files at once, or what appears to be at once. Gives you the illusion of running all that stuff at once. So 2 more videos after this one. I know it's been long, but it's a lot of stuff that we had to cover. So have a good rest of the week.